Lab 1, Charge Tape Experiment. Introduction. The purpose of this lab was to create a model of interactions of two charged objects, then create a computational model to approximate the excess charge of the system and charge exchanged. We used two similarly charged pieces of tape with identical dimensions and measured their interactions with each other. The experiment observed with initial conditions of 0.2794 meters long, 0.019 meters wide, a mass of 5.3 e to the negative 6 kilogram piece of tape. The tape moved 0.051 meters away from the similarly charged same dimension piece, allowing us to calculate a charge of 3.88 e to the negative 6 Coulomb charge for the tape's charge. Coulomb's law, Newton's second law, and Newton's third law. The lab required using Coulomb and Newton's second and third law. Coulomb's law represents and calculates the interaction of the charged pieces of tape, while Newton's second law and third law represents/calculates the forces on the tape and models their interaction, such as gravity, normal force, electric force, and tension. Surroundings. For the observed experiment, the system itself understudies the charged piece of tape for the first part of the experiment. For the second part of the experiment, it's the charged piece of tape, or tape B, that moved after having the other charged piece of tape move towards it from the bottom. Experiment. The experiment consisted of creating positively charged Scotch tape pieces and placing them close to each other to measure their reaction. One tape moves against the force of gravity, and we know from Newton's laws of motion that the force of gravity must be equal or less than the electric force. Therefore, we can calculate the charge of the tape as both charges are identical. The distance between was measured, and we found the mass of the tape, allowing us to use the force of gravity with our known values equal to our electric force equation. Data and calculations. To calculate the charges of the tapes, the electric force and gravitational force equations were set equal to each other. To find the unknown of Q, symbolic algebra led us to calculate that was equivalent to the square root of mass times gravitational constant times distance between the particles squared divided by Coulomb's constant. When applied with the known constant, the charge is found to be approximately 3.88 e to the negative 6 coulombs. Components. In my computational model, I initialized the conditions for the system and known variables. I then modeled the equations for gravity and electric force, as due to Newton's second law, we know gravity must be less than or equal to the magnitude of the electric force in order for tape B to move. The model then calculates the charge of the tape using the distance the tape moved with algebraic steps to find the final charge variable representing the charge of the tape. This model works on no assumptions that there's no air resistance, all of the charge is focused at a single point in the tape, and both charged tapes have the same charge. Sources of error. Possible sources of error include the tape not being the exact length we cut it. We also used an approximate mass per square inch, and the atomic amount in the tape was mostly off since we used moles, and we also might have left too much slack for the tape to move freely due to the force of gravity. Discussion. The lab ultimately exemplified Coulomb's law as well as interactions between charged particles. The pieces of tape moved attractively with opposite charges and repulsively with similar charges, hence proving the theory of electric fields and their attractions, as well as the way charged objects interact with neutral ones. What if and what does it mean? What if the charges of the electrons and protons were switched? Well, the tapes would react in the same way in the experiment as they were charged similarly, but the tape would react differently when exposed to neutral objects, as the charges would be switched and the objects would retain being neutral. Why is it important to handle the charged tapes as little as possible? Any interaction with charged or neutral objects causes the transfer of static electricity, the same way rubbing the pen in order to cause it to become negatively charged works. Charge for the tapes would be lost the more they are handled, hence ruining the experiment.